left it off last time. Where I would like to go next is actually explore the structure of an integer in terms of bits, and see how we can access all that and what we can do with those bits. But before that, one thing that I sort of promised I would do every class is do some sort of an algorithmic exercise that would sort of help you with your programming knowledge. So I was thinking that today we could do the towers of Hanoi. All right. So I'm gonna start saving it. All right, there used to be visualization or game. Let's see if we can find. Actually, I have this thing at home. I forgot to bring it. Would have been great. Let's see if this one works. Okay, it does. How? New game. I see. Okay, it's a bit slow, but still works fine. The purpose of the game is to move all the disks. These are disks, but we're looking at them from the horizontal perspective, right? So you can think of them as being donuts, right? And they fit on the pole, and you can see that they're arranged in increasing order of their size, with the smallest at the top, right? So we want to move all these disks to the third pole, probably tower 1 to tower 3, yeah. But at all times, we can only move a smaller disk on top of a larger disk, never a large disk on top of a smaller disk, right? And with this constraint, the solution is something like this, which I'm sure you know and you would find out. I would like to know that, is this problem familiar to you? How many of you have seen this problem before? Quite a few. Okay, that's good. Okay, because one thing I want to discuss, so the natural solution is recursive. One thing I would like to discuss today is how to remove the recursion, right? So this is the solution, all right? And there's a pattern to the solution, okay? So if I were to start a new game and actually increase this number to 4, all right, what do I do now? So can someone explain it as a bird's eye view? So previously we moved 3 disks. Can we take advantage of the fact that we already know how to move 3 disks? Yeah, something like that, right? So we know how to move 3 disks. We just saw the solution previously, right? And now the poles are completely symmetric. So if because the solution that we're showing did not take advantage of the fact that the tower 2 was in the middle and tower 3 was on the right, right? So if I at all times reverse the positions or exchange the towers in the moves, right? I'm going to be able to move all the disks from here, 3 disks from here, not to tower 3, but to tower 2, right? So essentially, if I can move disks from tower 1 to tower 3, I can move them pretty much between any 2 poles. I don't have a restriction on who's first, who's last. Right, so let's do that. So a previous time, in the previous round, I started by moving this disk from here to here. Because we are exchanging the 2, I'm going to move this one here, then this one here, this one here, and this one here. So now I'm replicating the solution that I was doing previously. And notice that, one, I have moved the 3 disks to the middle one, right? And this is what we're saying at the large picture level. We're saying we're moving n minus 1 disks from 1 to 2, from tower 1 to tower 2. Why? Because we know, we've seen it before, right? And actually that's how induction works. We always assume that we can solve the n minus 1 level problem. Now, notice also that in this exercise, the largest disk that sits here didn't bother us at all. Why? Because it's larger than any other disk. So previously, this pole would be empty when we had only 3 disks, right? The fact that the largest disk is there doesn't bother us at all, because all the other disks are smaller. So whatever we had as a previous solution still works, right? All the previous disks could be safely put on this disk, which is necessarily large, right? So we have the ability to decompose. Now we can safely move the largest disk to the destination pole, right? And then we already know how to move 3 disks, right? So the way we think about a problem, the way we decompose it is very important. So we already know how to move 3 disks. We're just going to apply that solution. And we're done, right? What happens, what's the base case? Because we're kind of talking about recursion, right? What's the base case? Can I have less than 1 disk? So if I have 1 disk, yeah, the solution is very simple. Move the disk from source to destination. What if I have 0 disks? Do nothing, right? It's already solved. Right, so 0 is easier to have as a base case. Okay, now we won't be able to do this nice animation in order to perform this, to implement the solution. I wonder if they have an automated animation. I mean, you will find solutions that will have the animation. So let's come and implement it. So what we're going to do as a solution is print the moves. Okay, we can't animate. I mean, we can't animate. We could, but it will take a lot longer to get to that point. I'm going to write the Hanoi function first, right? So the Hanoi function is going to return nothing, and we see how we denote a function that returns nothing, right? It's a void. Void represents the type that doesn't contain anything. All right, and we cannot have a data of type void, right? We can have a function that returns void, but interestingly enough, we'll see later, we can have pointers to void, right? Those pointers to void are not really pointers to nothing, are pointers to something that we don't care about, really. It's pointer, there must be some content which says that we don't care about what's there. We're going to get there, but we're introducing the keyword void. And now what should be the arguments? Obviously, the tower, the size of the problem should be 1 argument. What are the other arguments? Yes, so we're doing now another important thing that we sort of brushed under the carpets. I said that if I know how to move from tower 1 to tower 3, right, we pretty much know how to move the disks from any tower to any other tower, right? And this is actually what we call generalization. Seems very innocuous when we say it like that in a problem-solving setting, but we have to formalize the fact that we're solving a more general problem than the original one. We're actually not solving moving from 1 to 3, from tower 1 to tower 3. We're moving from tower A, where A can be any of 1 to 3, to tower B, where B can also be any of 1 to 3, as long as A is not equal to B, right? So that's a more general problem than the original one. And guess what? It's an easier to solve problem. So often, generalization actually helps. Many people think that, oh, we're going to generalize and I'm going to have to solve a more complex problem. No, actually generalization makes it easier to solve. You can find more patterns, or you can find more unifying patterns in a generalized setting. For instance, infinity is a generalization, right? Infinity is not something we see in real life, but since we can't put a bound on anything, we invent the concept of infinity, right? Now, if you go into mathematics, the concept of infinity simplifies mathematics. It doesn't make it more complicated, right? The fact that now that we have infinity, any two integers add up to another integer, right? So they have a very nice property, which you actually don't have with computer numbers, right? Two integers may add up to an integer that is out of range, right? So then you perform a modulo operation in there as well, right? So real world is more complicated than mathematics because it's more specific, not because it's more general. Cool. So let's. I'm going to denote the towers by A, B, or let's give them more better names. So this is the source, this is destination, and this is the auxiliary one. Now, in principle, we could derive the auxiliary from the other two. All right, and I'm going to ask you later how we can do that. Right. So I'm going to argue that this argument is actually not really necessary. You're going to have to tell me how we can avoid it. Let's start, right? So if n equals 0, so one way of coding this, which I'm not particularly fond of, is doing this, right? So we're trying to get rid of the easy case as fast as possible, right? So, and that's one solution. Another one, which to me seems more natural, is if n is not equal to 0. And then inside here, we say what the solution is, right? So what did we do previously? We moved n-1 disks from the source to where? To where? Auxiliary, right? We didn't move it directly to the destination, right? And then now, who serves the role of the auxiliary? What serves the role of the auxiliary? The former destination, right? That's the only one left. All right, so we perform this. Then we can print move disk %d from %d to %d \n, and then here we're going to have disk n, right? Disk of size n, but it's sort of understood, and we're moving it from source to destination, right? And then we're going to move n-1 disks from, where are the n-1 disks now? So when I did this, I took the smaller n-1 disks from where to where? From source to the auxiliary. So where are they now? On the auxiliary, right? So the auxiliary serves their role of source. We want to move them where? Here, right? Because this is where we wanted to move them from the very beginning. We're taking advantage of the fact that the largest disk is already there. Everything goes on top of it. And then SRC is going to serve the role of auxiliary this time. Okay? So we are using printf. Include stdio.h, and then let's provide and we can actually, I think we can just say this. We don't have to provide argument names. I'm hoping. Can't remember, actually. Vaguely I remember this could be possible, but if not, we're going to change it. And then we have to write the main. And we're going to have to read n from somewhere, right? So int arg c char star arg v, and we're going to do exactly what I did before. By the way, the names argc and argv, I told you, you can replace them with anything you want as long as you're consistent. Traditionally, they've been named this way. So we're going to have n equals a to I, and because of that, we're going to need to include stdlib. All right, argv 1, and then we're going to do Hanoi of n, and 1, 2, and 3. Okay. Now notice the fact that nobody compels us to put 1, 2, 3 here. We could put any numbers. We could denote our towers by anything we want, right? Also, we're not involving these numbers in any arithmetic operation, so they don't have to be integers. They can be strings if we so want. Right? Just that because they're integers, we're going to have a very easy way, assuming that they're always in the set 1 to 3, we're going to have an easy way to avoid the AUX, right? So I'm going to ask you later what that is. Let's, for the time being, just compile this, gcc -o hanoi.c. Really? Yes? Again? What is undefined? Yeah, it is, and we will get an error, and we should say int in front. That's very true. Save as. Oh, we called it towers. We are inconsistent here. Okay, so yeah, and so this works, right? So you can have a faster way of defining this. But you know what happens most of the time in practice? You're just going to go. You're going to discover that you're going to write your function, and you're going to discover that it's undefined, right? So you get the warning that it assumes the wrong time for it. So in most cases, coders, what they do is they just copy and paste this, right? And they don't bother to get rid of the variable names. All right. So you'll very often see function prototypes where you have argument names, even though they don't serve any purpose. So towers, and let's say 4, and we're going to have this set of moves. Okay, and I've done this so many times that I'm not going to. I should go now and demonstrate that this is a correct solution. I'm going to leave that to you to verify. You can do it on your own. How do we, if we want to not have this AUX? All right, what would you do? This auxiliary tower there. Because if I know the source and the destination, whatever remains is the auxiliary, right? What trick would you employ? Something that is very simple. So obviously, if I remove this from here, because that's what I want, right? then this occurrence of AUX and this occurrence will yield errors, right? So what should I replace this with? Or can I do something like int and write something there that would lead to a correct solution? Yeah, that's true, right? So we can, and we're going to introduce something new on this occasion. So one way it would be to notice that they add up to 6 and say that aux is 6 minus src minus this. Okay, but one thing coders don't like is these numbers inside the code without an explanation, right? There are only 2 numbers generally allowed in code, 2 numeric constants allowed in code without explanation, and those are 0 and 1, right? Whenever you need to use a number, for instance, a very frequent thing is converting number of seconds to number of minutes and hours, right? So you need to divide by 60, right? And you don't put the 60 in the code. You don't divide by 60, right? We want to create a symbolic constant. This is what we call it, a symbolic constant that makes it very clear what is the meaning of that constant. Why are we using that, right? So in this case, I'm going to introduce a symbolic constant, and I'm going to use this keyword define. All towers 6. And I'm going to use here all towers. Okay. Now the replacement, this is what we call a macro. Do you know what a macro is? What's the difference between a macro and a function? Yeah, that's a good point. And that's actually a very good point. I should have praised you for understanding the difference between compile time and runtime. And I want to ask, how many of you actually understand the difference between compile time and runtime? Have you heard this concept before? 3 of you. All right. So I was going in a different direction, right? So a macro is a form of reuse of text. It's not really a reuse of code. It so happens that we're working with code, but macros can appear in a variety of other contexts where the replacement is done in a manner that is called call by name, not call by value, right? So so let's say I'm going to replace here 100, well, I could say 12 minus 6, right? Which will still be a correct value. Okay? So what's going to happen at this point is that we're not going to see 12 minus 6 being evaluated and then this thing replaced by 6. We're going to see this thing replaced by 12 minus 6. Whatever text we put here, that text is replaced here. Understood? And that happens even with arguments, right? So I could say define macro, and a very typical macro, which we use extensively, is min, a, b, right? Which is often defined, we're going to reach there, a less than b, question mark, a or b, right? So this is min. So what happens is that wherever you see the use of min, it's not that you know, so let's say somewhere here I'm going to use min of 10 and 20, right? Let's say I do that, right? So it's not the case, and maybe I'm going to say 10 minus 5 and 20, right? So it's not the case that this value will be computed as a constant. You see, everything is constant here, right? This is a constant, this is a constant. The compiler could derive the constants, right? 10 minus 5 is a constant. So that's not what happens, right? The 10 minus 5 is will textually replace A, 20 will textually replace B, and what we have here, right, the replacement will be, right, 10 minus 5 less than 20, question mark, 10 minus 5, and B, and 20, right? So this is how this replacement works. This has certain advantages, but it tends to slow down the compilation, right? So we're in order to run our programs, we're doing two things, right? We compile, and then we run, right? So this command, if we have a lot of macros, is going to take long. Okay, but guess what? This command, we only perform it once generally. So now because we're learning, we're doing what? Compile, run, move on. Compile, run, move on. Typically what you do with a real piece of code, right, is compile, run, 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 run. You typically run it a million times and you compile it only once, right? So then you prefer to lengthen the compilation phase, provided that it can make the run shorter, right? Take less time, and because of that, you'll see macros being used quite persistently, especially in C. We're going to use a few, actually, here and there, every once in a while. The important thing is that they execute at compile time, all right, not at run time. So they're not really functions. So what we're doing here is essentially defining a symbolic constant, because we don't want that number 6 to be in the middle of the code without an explanation. Okay, and we can verify now that this continues to work. And guess what? Oh, okay. So I can remove it from here, and I can remove it from here. Oh no. I can remove the last argument. AUX stays here, right? I can remove the last argument, and I can remove the last argument from here. Am I doing the right thing? Probably not. Okay, so I can remove the last argument, not AUX. Okay, so and then we want to remove one argument from the prototype as well. And finally, it works, and this works as well. Is this clear? Okay, so now how do we get rid of recursion? Louder? We probably will have to use a for loop, but there's something more important that we need to use. Okay? So you see, one very interesting thing that happens with recursion is that as I go from this call to this call, the value of n that we received here is preserved, right? So I'm going to go into the nested call. When I'm coming back from that, I'm going to have this value of n preserved, even though the first argument in the nested call is different, right? So we're going to have many instances of calls and many instances of the argument n because of that, right? So how do you think that the compiler and the program keeps track of all these instances? Louder? Yes. Yes, exactly, right? So it uses a stack, right? And if you haven't heard what a stack is, you might have seen in a restaurant that plates sit in some sort of a hole, right? The bottom of the hole has a spring, and the spring is calibrated in such a way that you only see a small number of plates above the tabletop, right? And everything is inside. But as you keep lifting the plates, right, because you're making the weight is smaller, right? Then the spring pushes them up, and you can take away all the and use all the plates, right? The important thing there is that that's a stack. You have a last in, first out order, right? So the last plate that was put in is the first to be taken out at any point, right? So if you think about that, this works for our arguments as well, right? So the first argument that we push into the stack is 4. From 4 we go to 3. So guess what? 3 goes on top of 4, right? And it pushes it down, right? And then 3 goes to 2, right? From Hanoi 3 we go to Hanoi 2. So 2 goes on top, right? And then 1 goes on top, and then 0 goes on top, and then for 0 we have nothing to do. So then when we come back to 1, we remove the last n. So we have now 5 n's, right? From 4 to 0, they're all in the stack, right? At the top there's 0. When we come back from Hanoi 0, we remove the n equals 0, and what's left there is the n equals 1. So the last but one instance of Hanoi has its n variable intact, all right? And then it doesn't, you come back from the first call, you execute, you print out, and then you go again into a Hanoi 0, and it goes, the n0 goes again on top of n1, and then it gets removed, and then you're returning from n1, so this one gets removed, and then Hanoi 2 gets its n intact, right? So this kind of stack discipline is very important, okay? So we're going to use something like this. So we're going, as we did last time, let's call this Hanoi recursive, and let's rename it completely and create a Hanoi iterative. Sorry, this should be recursive. Hanoi iterative. And we're going to, this time we're moving from 1 to 3. We actually don't need any other arguments, okay? And we're going to employ a stack. And the only way we know how to use a stack right now is by using some arrays. And this is where we introduce arrays. In principle, there should be a single array of structures, but I don't want to talk about structures yet, so I'm going to have multiple arrays. So these arrays are going to hold encodings of problems. And we have 2 types of problems here. There's a problem of recursively moving more disks, even though it's iterative, recursively moving more disks. And there's the problem of printing out the move of one disk. Okay? So what are we going to do? What we're going to do is every time we have to solve a problem of the type of every time we have to solve a problem where n is greater than 0, that's a problem of pushing. We're going to just decompose that problem into several, right? So we're going to push on the stack a problem of size n minus 1. We're going to push on the stack a problem of size, and that has to go in reverse order. So we're going to push this problem first. Push on the stack a problem of moving n minus 1 disks. Push on the stack a problem of printing, and push on the stack a problem of moving again n minus 1 disks. Right? So we have two arguments. So we're going to have an int size, and I'm going to say 20 here to be conservative. We're not going to be using 20. So this is an array of 20 elements of integers, right? Int sources 20 and int depth 20. Okay, so int current problem equals -1. So we're going to push the first problem. Okay, so in pushing the first problem, and in doing that, actually we can use 0 here, and we're going to have that size 0 equals n, src 0 equals 1 to 3, right? 1 src of 0, destination of 0 equals 3. All right? So this is my initial problem. And now, while current problem is greater than -1. -1 means that our stack is empty. Okay? So we're going to extract the current problem. What's the current problem? Current size equals size of current problem. Then current source equals source of current problem, and current destination current problem, right? And if current size is greater than 1, right? So I have a problem of size greater than 1. What do we do then? We decompose this problem, right? So looking at the recursive solution, let me just make this a bit bigger. Looking at the recursive solution, right? So we should do this first, then this second, then this third, right? So in pushing them on the stack, I'm going to push this one first, then this one, and then this one, right? So then when I pop them from the stack, the one that is at the top is this one, which I have to perform first, right? So now it's gonna take a little bit. So one thing that happens after we have removed the problem from the stack, right? This is not the top problem in the stack anymore. So we're going to say that current problem minus. Okay, that's another thing. So now we have to push this problem, right? So we're going to say, I'm just going to copy and paste from here. Right, so inside here, we have to do current problem ++. right? So size of the current problem is current size. What's the value here? Current size minus 1, right? Then source for the current problem, right? Looking here, the source for the current problem is auxiliary, right? So we are going to, again, construct an auxiliary. Actually, let's construct it inside here. I'm going to say int aux equals all powers minus current source minus current destination, right? I think I was premature with copying this one. So source of the current problem equals aux, right? Destination for the current problem equals, looking here, is the same as the destination, right? So it's current destination. Okay, so what we have done in these lines is we have pushed on the stack this problem. Okay, then we're going to push in this problem. So this is a problem of size 0. Okay, so again, we're pushing a new thing, current problem plus plus, right? We're adding an element, and then we're going to have that the size of the current problem equals 0, right? And the source of the current problem and destination of the current problem are the same, right? So this should be current source. Okay, we're moving, we're looking here, right? So the source and the destination. Okay, so then the last thing that we have to do is push this one. Clear? So I'm going to, again, copy these lines. Copying and pasting is not a very good thing, but with our current knowledge, this is pretty much how far we can go. And I just want to clarify this aspect that recursion is not always needed. So we are looking at this one. So the source is the same, the destination is the auxiliary, right? So the source is the current source, and the destination is the auxiliary, right? So we have pushed the 3 problems on the stack. Now, what if current size is greater equal 1? So let's say greater than 0. Sorry, greater equal 1. Sorry, this is a problem of size 1. Let's make it the problem of size 1, right? So if I have a problem of size 1, what do I need to do? You see, if my current size that comes from here is a problem of size 1, what I have to do is print, right? So I'm just going to copy this line. And then this is the current source. And this is the current destination. They're initialized at the top, right? So current source is initialized here. and they need to be declared, right? Which we can very easily do. Sorry, I'm very much in Python mode these days. Okay, this should be fine, right? So what's going to happen at some point? So we're starting with a stack that has one element, right? And we're going to keep processing as long as the stack is non-empty, right? So we denote the fact that the stack is empty when the current index at the top of that indicates the top of the stack is -1. Okay, so at some point this is going to happen, and we're going to perform this guy. This guy is -1, right? At that point, better be that the last problem we solved was a problem of size 0, right? So we're going to go here, print something, and then come out of the loop. So this should pretty much be it. So we can close the while loop, and we should be able to close the function. This should be void. And I'm going to take this and put it here. And this is the prototype. Okay, oh, I didn't scroll low enough. So let's call it. So we're going to say printf recursive solution \n, and then we're going to do iterative. And Hanoi iter of n. And let's see how many errors we have. Okay, I forgot a semicolon at line 34 here. Okay. So we're moving the wrong disk. Because here we shouldn't have n. We should have current size, right? Okay, so let's see whether we got the same solution. Right, so 1, 2, 3, 1, 2, 2, 3, 2, 2, 1, 2, 2, 1, 2, 3, 2, 2, 3. So it seems that we're replacing, oh, so one thing that we did wrong here in the recursive solution actually is we didn't indicate properly the source and the destination. See, we have the source and the destination. So we want the source to be 1 and the destination to be 3. But when we called it here, we called it with 1 and 2. So this should have been 3. Okay, correction again. And do we get the same solution? Right, 1 to 2, 1 to 3, 2 to 3, 1 to 2, 3 to 1, 3 to 2, 1 to 2. The last ones are 1 to 2, 1 to 3, 2 to 3. Right, so they look the same. Cool? Does this make sense? Okay. We're going to learn later how to use a technique called encapsulation. We're going to learn about structures, and we're going to use a single array of an object that can have multiple components, right? Which will make the code a little bit cleaner. But by and large, is it clear that recursion can always be replaced by iteration? I can use this anytime with anything, any kind of solution. I can apply this technique and it will work. Right? So instead of performing the call, you see, having the recursive solution was still essential. This is a difficult problem to solve unless you use recursion. All right? And it's also a difficult problem to solve if you don't generalize, if you don't add these two arguments and solve a more general problem, right? But the important thing that we did in converting recursion to iteration is we still looked at this sequence of events in reverse order, and we say, oh, I'm not going to call the function. I'm going to say, oh, I have a problem to solve. So I'm going to create an encoding of this problem, and I'm going to put it on the stack. So what is the encoding of the problem? Well, the element at the index called current problem in each array will give me here the size, here the source, here the destination, right? Exactly these three arguments. Right? So I'm going to have an array of all the ends, an array of all the sources, an array of all the destinations, right? But they're organized as a stack. So I start from 0, and every time I want to add, I have a current position, and every time I want to add, I'm going to move 3 positions further, right? Every time I add a set of problems, I'm going to move it this to 3 times for 3 elements. I'm going to put 3 problems in the stack, right? 1, 2, 3. I don't solve them right now. I'm going to say, oh, I'm going to have to solve these problems in this order. Then I take the first problem from the stack. You see, I go around the loop and I take the first problem from the stack. I say, oh, from my current problem, this is the current size, this is the current source, this is the current destination, and I have removed it from the stack. Because I have taken stuff from the stack, I'm going to move 1 position backward, right? I'm going to put my cursor to what is now the top element of the stack, right? And then I'm going to look at my problem. If my problem is of moving more than 1 disk, the only thing I can do is decompose it. I cannot solve it immediately. However, if my problem is a problem of moving a single disk, that's something that I can solve easily. So I'm going to go and print the line and move on. Okay? So if you think carefully of how this works, it mimics it's completely isomorphic with the set of recursive calls. Okay? So you have this. This sort of will demystify the fact that it's not good to use recursion. It is good to use recursion because without an initial recursive solution, we wouldn't have gotten here, right? We conceived of the solution recursively, and then we applied a standard technique to make it non-recursive. Nevertheless, as somebody outlined last time, you don't want to push code to production. You don't want to have code released that has recursion inside. Because recursion consumes non-deterministic amounts of memory, and you don't know what your code is going to run on, right? And therefore, you don't know the limits of your code in this way. How much memory is it necessary to run? Well, it depends on how much data the guy has, right? And what operating system he's using and so on, right? So you open a can of worms if you do it, right? So when you indeed release code, you should take advantage of techniques like this to make your code non-recursive. Questions? So one application when we talk about structures is going to be to go back here and make it nicer by using structures. Okay? So importantly, we have introduced arrays. Okay? This is an array. It's something that you know from other programming languages, right? Everybody has seen an array in a different programming language before. Yes? Okay, nobody seems too worried, so I'm guessing everybody has done that, has gone through the experience of working with an array. Okay, let's look at bits. So, new file. All right, I'm going to call this one bits. So, let's print all the bits of a number. We're going to read a number from the input, and let's try to print all its bits. At the same time, so let's start by not printing its bits. Let's start by printing all its digits. Let's assume that number is always positive, and let's try to print its digits. That function actually exists, and it's called I to A. We've seen A to I, right? ASCII to integer. There is a similar function called I to A, integer to ASCII, that performs the print. Nevertheless, printf performs that conversion as well when you use %d as a specifier. But let's do it from scratch. So that's interesting now, because we have to use an array of characters as a string. All right, so let's do that. So let's start with include all right. You're noticing probably now that both include and define start with a hash. All right. That's because these are not processed by the compiler. They're processed by a different piece of code, by a different program called the preprocessor, which is invoked by the compiler in the background. Right. It's transparently invoked. But there's a step between this file and the actual file that gets compiled. Right. And that file can be exposed. And that's how the preprocessor makes the difference, knows the difference, right? Everything that starts with hash, it's its job. Everything else goes to the compiler. The preprocessor is relatively dumb. All right, include stdio.h, and we won't return an array yet. So we're going to have a global array, which we call digits. And let's say we put 20 here. And I'm going to initialize this array with 21. Might be too many, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So better more than fewer. So 20 spaces. All right. Why did I use 21 locations? Why do you think I used 21 locations? For a string of length 20. Louder. So the length is 20. I just counted 20. I hope I counted correctly. I might have been wrong, but the intention was to put 20 spaces there, right? Why do we think I have a 21 here? So how do I know where it stops? So there's a backslash 0, right? So again, arrays in C do not encode the size. There's nothing in this that tells me the size, right? Whereas in most modern languages, the size is an intrinsic part of the array. The array is an object that has the elements and its size. But the way you know how long the array is up to you, the coder, right? You have to encode it in a separate variable. You have to keep track of it. one way to do it for strings. So a string is an array of characters, and one way to say that, oh, the string is up to here, is to put an invisible character whose value is the integer 0. All right? So typically, because we use character notation, we represent it like this, \0. Okay, because 0, this will be the digit 0. Right? So \0 is the ASCII character whose integer value is 0. Right? So that denotes that this is where the string terminates. And most of the time, whenever we work with strings in C, we're going to keep processing until we encounter this \0 character. Right? It's a terminated character. This takes an extra character element. Right? So whatever you see here, right, is one less than the actual size of the string. Now, this is a string literal, and normally a string literal would be something with some characters inside, but just like they chose the characters to be spaces this time, so you still see this big empty space. It's not empty really, it's this space character in there whose value is 32 decimal or 20 hex. We're going to talk about hex in a minute, right? And then this literal, the compiler will encode this literal by putting all the codes in the memory and then at the end adding a \0 automatically. All right, so the \0 is there. All right, and then if we say 20 and we put 20 characters here, the compiler might complain, right? You want to have always one extra character that can hold the terminate. So let's print the digits. And now we're going to take a number and fill this string with digits, right? Void digits, void fill digits, and n. All right. Where do you want to start filling this array? From the beginning or from the end? So do we start at the end going backwards, or do we start at the beginning going forwards? What's easier? Louder? From the start? What's the easiest thing to find out from an integer in terms of decimal digits? So I have an unknown value. Completely unknown value. What's the easiest thing to find out in terms of digits? Which digit is the easiest? Louder. The last one, right? How do you find the last one? Modulo 10, right? So that's a very simple operation. How do you find the first one? You have to kind of know how large the number is, right? So let's go from behind, right? So I'm going to start with a counter int I equals 19. Why 19? Because the first element has index 0, right? And then the last one will have size index 19, right? The last guy here, this guy, has index 19, right? Pardon? So whenever you have n elements, they go from 0 to n minus 1, right? And if you have 21, they're going to go from 0 to 20, 20 being the \0. I don't want to override the \0 because I lose the terminator, right? So the last character in the string is not the terminator, it's whatever is before the terminator. Okay? And now, what I'm going to do is, while n, and we're going to find better ways of doing this, n is greater than 0, and we're going to assume that it's positive. Okay? So I'm going to say current digit equals n% 10, right? What do I do with this current digit? Okay, let's not confuse you completely. So digits I, this is the current position. I'm going to fill from backwards, right? Last digit first, second last second, third last third, right? So now, can I say D here? Can I say D here? That confuses the heck out of people. Always. No. Eventually, I want to print this, right? So I'm going to replace every space, not every space. I'm going to start from here and replace spaces by digits, right? Digits meaning printable characters, right? This D is a value between 0 and 9 inclusive, right? What are the digits that are printable, the digit characters? Again? All right, so let me try to find last time. I think we were here. So we're saying that these are non-printable characters, right? From 0 to 32, when we are printing these, we're getting all sorts of... Louder, please. Yes, exactly, right? So I have to put there, where am I? So what I put here is something between 48 and 57, right? How do I get something between 48 and 57? Louder. Good, that would be one solution. Not one that we would like very much, but it would be a correct solution. How can I replace 48 with something that is a lot, that shows the intention of this code? Good, very good. Yes. So I could use this, right? So I take the ASCII code of the character 0, which has the value 48. So remember, this is 48, integer 48. That's the integer 48, all right? It's just another way of saying integer 48. But the beauty of it is that you never need to know that this is the integer 48. You're completely discouraged from knowing this correspondence. All right, so I take whatever code, whatever number the ASCII code for 0 is, and I add the value of the digit, and I'm going to get a printable character. Does that make sense? So the value of the digit and the printable ASCII code for the digit, there's a correspondence between them, but they're not the same thing. What do I do with, what do I do with I now? Again? Increase by 1, very good. Now, not only in C, but in many other languages, instead of doing I minus minus here, I could put it here. Everybody knows, how many of you have seen this before? So nowadays, 1. Okay, so this is actually quite discouraged. It's an interesting thing. It's a can of worms from for many kinds of bugs. It will open the can of worms for a lot of bugs. And nowadays, people are kind of agreeing that this is discouraged. In the old days, everybody was trying to write short code and concise code. So you can say I minus minus, and you can say minus minus I. Then I minus minus is executed after the entire assignment at the end. Minus minus I is executed before, right? So you can take advantage of this in a variety of ways, but most of the time somebody else comes later and changes the code and doesn't understand exactly what the intention was and introduces a bug because of that. So What do we do with n? So now we have the last digit. How do we prepare it to get the second last digit? Louder, please. Divide by 10. Very good. Everybody understands what's happening here? And I'm going to write it here because I want these two to be very close to each other. n% 10 and n divided by 10. I want them to be very close, right? So because of this, n decreases. At some point, it's going to become 0, and we're going to exit the loop. Okay? So let's do the main. Int main int arg c char, and we're going to say print f the digits of the input number are %d \n, right? And here we're going to be very concise. We're going to say fill digits a to I of argv1, right? So now you can see that we can nest functions, right? So printf calls fill digits, which in turn calls a to I, right? We can nest them at any level we want. Okay, so now this is going to be a relatively stupid function because it just prints exactly the same thing we read from the input. Oh, sorry. With symbol clang, mine. Oh, I have not saved. So how can we get less than? So if we assume that we're starting with a positive n, which might not be the case, right? We can always break the contract and input a negative n, right? So we should, in principle, all the time, if we were good coders, we should actually put a test here and avoid right, provide an error message for that. But we're trying to save a little bit of time and all right. But then n and 10 are both positive, right? So there's no possibility of getting a negative number out of two positive ones when you do division or multiplication, right? Include stdlib. No, so it will reach 0, right? It doesn't have to go below 0. It has to reach 0, which will, right? Right, it will fill the. Oh, okay, that's very true. That's very true. So actually, that's very true. Good point. So we're going to call this, and then we're going to print digits, and then you cut me again. This should be %s. All right, because we're printing a string. I think we've seen this before, right? And actually, that's why the error message was there. So it's very good to know that you're following. So let's take 1, 2, 3, 4, right? And we get the output. Notice how far it is, right? We have only placed one one space here. Yet here we have so many of them. Why? Well, because here we have 20 spaces. Actually, if you're going to count from here up, if I could select properly and use the mouse properly, it would be good, right? If I'm going to go up to here, you're going to count exactly 20 spaces, right? This space that is between the colon and the start of the marking is this space right here, right? And then we have all the 20 spaces of the string. Now I'm going to, I mean, we can put a larger number here, right? 5, 6, 7, 8, 9, and we see that all of them are represented 0, right? And at some point we're going to get an incorrect number, right? 1. Okay, so we have exceeded the 32 bits. Clear? So what we do is we take this large string filled up with spaces, and from backwards, going forward, from the end, going backwards, actually, yeah, we fill up all the digits one by one. Okay. Now we haven't talked about that yet, but perhaps it's a good time to introduce it now. We can use larger numbers. Instead of 32 bits, we could use 64 bits. So this is actually not a standard feature. It belongs to, it was introduced by GCC, but nowadays it's pretty much standard, right? So I can use a long number. All right, just that here I'll have to use an A to L, I think, and let's see if this works. So now automatically this is a 64-bit number, so it's capable of larger values. I'm hoping I'm remembering correctly. And there we go. Now we're not limited by the 32 bits that we had before, so we can actually add some more digits, and they will be correctly represented. But there's a limit to this as well. I'm not sure whether it fits. Oh, okay. So see, we got there because this is not the actual value anymore. Right? So this is as many as we can get, which is probably about 18. So 20 spaces here was pretty much a good estimate. Cool? Understood? Very quickly. How do I get the bits instead of the digits? So let's call this one fill bits. So now we know exactly how many. This is a 64-bit number. I'm hoping nobody has a problem with 64-bit numbers. It's just another size. Right. Everything is that we are doing with 32-bit numbers is still possible, but we have more bits to tackle. So I'm just going to add 20 more spaces. Actually, 20 more spaces is not going to be enough. So we're now at 60. 1, 2, 3, 4, 5, just to be on the safe side. Right. So we have potentially 64 bits. Oh, I'm sorry. Actually, I shouldn't have done this. Let me go back and let me create a copy of this, which has 64. So these are going to be bits. And here we're going to have 65. All right. And hopefully we put 65 spaces there. So now tell me, what do I need to change here if I want to fill the bits? Come on, it can't be that difficult. So base 10 versus base 2, just bases. right? So we count in base 10 normally, but the computer counts in base 2. So what do we replace in here? Okay, modulo 2 division by 2, right? And we're going to have zeros and ones. So whenever n we perform n% 2, we're going to have d either being 0 or 1, right? So this is still correct. Everything else is correct, right? So we're doing it this time this way. So I want to show that it's correct. So let's compile. And another thing before we compile is let's copy this and say the bits. So the input number are percent s, and here we have the bits. Okay. And oops. Oh, another thing that we need to do is this should be bits, right? We're filling up this array, which is what we're printing here. Okay. We should also call this function. I think it's a bit late for all of us. Segmentation fault. What did you say? Did I count incorrectly? Oh, this should be very, very well, very good. This should be 65, I think. I'm hoping I counted correctly because I just copied and pasted. Yeah, so now you have the binary number, right? How can we verify that this is correct? Well, I'm going to give you one. There's this calculator called BC-L. It's a command available in all Unixes, and it just performs arithmetic. So you can do 1, 2, 3 plus 4, 5, 6, and it will just give the result. It has arbitrary precision arithmetic, including for fractional numbers, for floating point numbers, right? So one a neat thing that you can say here is say O_base equals 2. We can make it whatever you like, and then I can take this number, and a single number is in itself an expression, right? So the value is itself, and normally it will just print itself, but since we change the output base to 2, it will print. No longer? I thought it, or is it O base? Ah, yes, right? So now we can compare, right, and see that it's correct. All right. So you can also do it in Python, right? So you can format a string and print numbers as binary in there. And actually, if I remember correctly, we should be able to do 0%b. Haven't done that in a long time. Print f. So let's see if that works. Verification %b and backslash n, and we're going to say a to l argv1. Let's see if this works for us. No. Okay, very quickly. Must be. Oh, it seems that there isn't. Very strange. So everybody will give you a function to convert because they want to score points, right? On Stack Overflow, but there's no. So it doesn't matter that it's not the answer you want. They were still provided there. Okay, so sorry, I misremembered. But this is it, right? It's already past the hour, so I'm gonna stop here. The interesting thing is that we have much faster alternatives for these two operations, and we're going to discuss this next time. How do we take the modulo 2 from a number if the base is 2, and how do we divide by 2 if the base is 2, right? You might know already the answers to this, but they're a lot faster, and we should learn how to do that. Cool, and that pretty much will conclude our exploration of integers, and then we're going to go into floating point numbers, and we're going to do the same. We're going to look at the bits inside the floating point number, both for doubles and for floats, which are, one is 32 bits, the other is 64, and try to understand exactly what's there. But we already understand two different encodings. We understand that of an integer, remember that, and we understand that of a printable character. And we understand that we have to convert between them, right? And we understand that it's up to us. The compiler doesn't help us a lot, right? In all the other languages, there is assistance for that. There's a type character which is not integral. It's not something you can do arithmetic with, right? So whenever you're trying to mix characters and integers, the compiler will slap you on the wrist, and that's a good thing, right? And the fact that it's missing from C gives you more power, but then you have to have more responsibility, of course. And there I coded Spider-Man, right? Cool. Thank you so much. See you next time.